Thank you, Pernille, and thank you also, Jans Christian, for organizing these CHEM talks. I'm very happy to be able to talk to you today over this lunch break. And as I actually joined the department quite recently, I thought this is a very good opportunity to tell you a bit, give you a general idea of what I have been interested in and what I'm currently, what are we currently doing here at the inorganic section in the department. So I chose for today a very general title for the talk. And I think from this title, maybe the first question is, why should we study quantum materials? And I might be a bit biased as a material chemist, but I think there is no doubt that materials are a driving force for technological advances. And in order to make these technologies possible, we need to not only be able to create materials, but also to understand them. And we do have pretty good understanding of a broad range of functional materials. For example, we do know pretty well the electronic and optoelectronic properties of silicon. And in this way, we have been able to fabricate very sophisticated microelectronic devices that we use daily in our smartphones, our computers. We have also been able to integrate them into photovoltaic devices, for example, for solar cell conversion. But there are certain class of materials in which the strong interaction between electrons give rise to cooperative electronic phenomena that are much more complicated to understand. Maybe one of the most representative examples are superconductors, where electric current can flow without any resistance. And we can, for example, use this to create very strong magnetic fields to design a futuristic way of transport, but also, for example, for medical applications. And even more nowadays, this class of materials also promise to enable a completely different way of computation that is only start being explored. So if we want to develop these complex quantum materials, surely this will require a strong collaborative or multidisciplinary effort, because we need to understand first the structure and chemistry of these materials, but also we need to be able to link it with the emergent quantum phenomena that we will expect. And in order to make this link, what we actually want to be able to do is to control and understand the interplay between these different degrees of freedom that we will have in these materials, and drive this interplay towards the applications we are interested in. So in our case, as a solid-state chemist, our work mainly relies on synthesizing these materials, preferably in single crystalline form. And the synthetic methods that we use for this to prepare these extended solids are quite different to the ones that we will use in molecular chemistry. For example, or the main difference is that usually we will require to use much higher temperatures in order to allow diffusion in solid state. And as examples, we will, for example, use reactions in vapor phase using these closed quartz tubes as reaction vessels. And in this way, try to crystallize our materials from the vapor phase. We can also try to dissolve our materials in some metal salt at high temperatures, usually between 500 or 1,000 degrees. But sometimes these temperatures are still not enough, and we need to go even higher. And for this, we can use more advanced or sophisticated equipment to, for example, melt our materials using infrared light. And in this way, melt our materials at temperatures up to 2,000 degrees. So we will use these different types of synthetic methods. And once we have obtained our single crystals, ideally, is when actually the real fun starts, because then we will perform a detailed characterization of these materials, aiming to solve not only the crystal structure and composition, but also the electronic and the physical properties. For this, we will use diffraction methods using electrons, X-rays, and also neutrons, the associated spectroscopies, and we will do physical property measurements. And these are methods that we use in-house, but that we can also access eventually at large-scale facilities. And why do we need this, all this information? Is because only by having this whole picture of the material structure and properties is how we can actually close this loop for materials discovery by performing here an iterative process of linking properties and structure, and through these relations try to identify target or electronic motifs that will allow us to actually design new materials. So I have been employing this methodology to a wide range of functional materials, but today I will mostly show you some examples of which kind of chemical modifications can we use to access either superconductors or new low-dimensional magnets. But before, I think I should tell you a bit about myself. How did I end up here and what I had been doing for the last years. So I did my bachelor in chemistry and my master in physics, both at the Complutense University of Madrid in Spain. And I stayed afterwards for the PhD. Which was actually pretty long, but this was kind of a standard at my university. And indeed, it was a good thing because it allowed me to also spend several short-term stays abroad, and so get a bit more, a broader picture of research interest. So I spent the first 3 months at the ASRF working or learning some X-ray absorption spectroscopy. And later on, I did 2 short-term stays of 3 months each at the Kyoto University in Japan. Then after defending my PhD in 2021, I went abroad for some postdoctoral studies. And I went to Switzerland, where I was working first at the University of Zurich and later on at the University of Geneva. And from there, I joined the department in spring last year. So I thought for today, I will just give you a small hint of some of the topics I've been working on through this process and how I'm trying to now merge this background into the future research here at the department. So in particular, I would like to focus on the potential of using low temperature reactions and moving beyond oxygen to other anions as a way to try to attain a more directed or controllable approach for materials design, moving a bit away from the usual thermodynamic constraints that we have when we prepare solid state materials. So my first research topic was working on unconventional superconductors at my home institution in Madrid. And I was extremely lucky to count with the supervision of Miguel Alario, who was really a pioneer in establishing solid-state chemistry as a discipline in my country. And I would say that his main obsession, science-wise, was definitely cuprate superconductors. And I cannot blame him because I think it was really one of the most exciting topics to work on as a solid-state chemist. Particularly after the discovery of cuprate superconductors back in 1986, because this was followed by really an unprecedented global race to try to raise the critical temperature by chemical substitutions. And he was actually pretty involved in this fun race. But you can imagine that I joined the party quite late. And by the time I started my PhD, it was actually not easy to figure out what we could further contribute to this topic after this enormous amount of work. And maybe to put it a bit into context, what was my problematic at the time, this cuprate superconductor has actually very complex crystal structures, layered. But if we look at this system with a physicist mindset, we can actually simplify the problem and focus only on the superconducting planes, in these copper-oxygen planes, and assume that the rest of the structure will just be a charge reservoir that will supply some holes for conduction. So in this way, the problem is reduced to a very simplistic toy model where we have just a square net of copper spins which are localized and antiferromagnetically coupled. And superconductivity will emerge when we introduce some holes for conduction into these planes. Of course, one cannot forget the chemical picture, because actually these holes are not at the copper atoms, but are actually oxygen holes. But okay, still this simplification works excitingly well, because by considering only this hole doping level as the main factor for superconductivity to emerge, we can actually systematize most of the physical properties of these materials. And we see how, as a function of this hole doping level, we have a complex coexistence of several electronic phases which compete or precede each other. But at the time where I was approaching this topic, we realized that actually most of the work was focused on this low doping region, whereas the highly doped region remained virtually unexplored. And there is a simple reason for that, and is that chemically it is very hard to access this region of the phase diagram. If we look at the prototypical YbCO compound, there is a maximum oxygen that we can actually incorporate in the structure. And this means that there is a maximum oxidation state that we can reach, which is already pretty high for a copper atom. So our idea was, let's try to replace copper by other transition metal, which could eventually allow us to introduce more oxygen. And in order to force iron to adopt also a pretty high oxidation state, what we did is to try a low temperature approach using ozone as a strongly oxidizing agent that we were generating in situ. And in this way, we were actually able to increase the oxygen content almost up to 8 and stabilize still superconducting materials at very high doping levels. And I think you can realize that I'm putting here very precise numbers for the oxidation states and for the oxygen content. And this is actually comes from a very detailed characterization of both the crystal structure at the local and average range, also of the electronic structure, for example, by looking directly at the amount of holes that we have at the oxygen atoms, and through a measurement of the physical properties, where we can actually see how we can go from an insulating materials to a superconducting materials, which actually show zero resistance. So with this information, we could construct a new phase diagram or place our compounds in the conventional phase diagram and see how, with this methodology, we could actually achieve higher doping levels and still show superconductivity in regions where we would not expect. And maybe before moving a bit further, I would like to stop for a second, because I'm sure that some people in my floor would ask me about this iron 4+, and it is indeed a not very usual oxidation state for iron, and it is actually not very stable, because if we assume this oxidation state for iron in an octahedral crystal field, we'll actually have here some electronic degeneracy that the system will like to release. So one way that the system have to lift this degeneracy is to actually undergo a charge disproportionation process and be present instead as a mixture of iron 3+ and iron 5+. And there are quite a few examples of this process in complex oxides. And what is to me even more beautiful, one can even, by selecting the proper composition of the proper structural frame, achieve different charge ordering patterns in a pretty controllable way. But the question is, can then we actually stabilize this iron 4+ in an oxide? And the answer is yes. If we manage to have a structure that is not too distorted, so that we can have extended enough covalency, we can actually make these electrons participate on itinerant bands, and in this way retain the nominal iron 4+ oxidation state down to base temperature. And these materials are even magnetic. In the literature, we could find only 2 examples of this, while our compound was then a third example so far of magnetic properties of iron 4+ oxides. So beyond the interest on discovering new magnetic compounds, we need to remember that this compound was actually superconducting. So actually, by using this low temperature oxidation approach, we were able to design a material in which we have magnetic monolayers of iron 4 plus cations alternated with our superconducting blocks. So this provides an ideal framework to actually study the interplay between magnetism and superconductivity. And this is a topic that I keep working on it. You can see that I keep still publishing results from this time, and I think I will never stop working on these cuprate superconductors. But okay, beyond romantic feelings about it, one moves forward. And this made me realize that these low temperature chemical approaches are very promising to stabilize new metastable phases. And to learn more about this, I moved to Japan for this short-term stay to the group of Professor Hiroshi Kageyama, where they were actually pioneers in developing these methods to attain more controllable ways of preparing complex solid-state compounds. And in particular, they were very interested in developing topochemical reduction approaches. So here, what do I mean by topochemically? What we would actually like to do is to retain the structural topology of our lattice intact by working at a temperature where we can only allow the anions to move while the cations remain frozen. So this is something they were working on for quite a while. They had a beautiful example of how you could reduce an iron perovskite by using calcium hydride at very low temperatures. I know this is not low for many chemists, but in this context, it is actually pretty low. And in this way, they could stabilize infinite layers of iron oxide who were still magnetic with pretty high critical temperatures. And as at the time iron was certainly my favorite element, I definitely wanted to dip further into this method and try to design more target low-dimensional iron oxides. So the potential of this method was indeed demonstrated. You could select different precursors, and in this way really anticipate which product will you get. And in this way, you could, for example, design different access different dimensionality on these compounds from infinite 2D layers down to spin chains with intermediate ladder configurations. But I realized that here we were all the time cutting the dimensionality on the perpendicular direction, we could say, but there was no example of how could we split these layers in this direction. So for this, I thought, okay, let's increase a bit more the complexity of our initial phase. What if we try to introduce some cation order on our precursor? And this is something that we can actually do if we replace part of strontium by a lanthanide. For certain sizes of the lanthanide ion, we can get a layered order of these A-side cations. And then when we try to reduce this order compound, what we observe is that the rare earth or the lanthanide layers actually undergo a structural reconstruction to release the strain that they have in this mismatch and come from a rock salt to a fluoride configuration, and they leave behind a pair of two infinite layers of iron. So we also studied the effect of the electronic properties of this structural reconstruction, but to me the most interesting point is that in this way we show how combining this low temperature approach with cation order, we could extend this family of compounds and actually provide or close the gap in the dimensionality. So I think with these two examples show that actually this low temperature approach for the synthesis of low dimensional magnets is actually very promising, and made me want to explore a bit more how to access low dimensional materials. And for this, I was already finished with my studies, so I decided to go to Switzerland, where to the group of Fabian Vonrohr in Geneva, to learn a bit more of crystal growth and also to explore further the physics of low dimensional systems. And this was really an exceptional place to work. I got in touch with other class of unconventional superconductors, for example, in intermetallic systems. But I also had the opportunity to work closely with exceptional crystal growers, and even further to access state-of-the-art infrastructure at the Paul Serrer Institute, where we could combine both X-ray, muon, and neutron experiments on the same compound at the same place. And if regarding the topic, I wanted to work on low-dimensional systems. So I think one of the most timely materials to work on at the moment are actually van der Waals systems. So these are materials where they have inherently this low dimensional character. They are composed of covalent layers that are bonded together only by van der Waals forces. So these allow us to exfoliate these materials, either mechanically or chemically, and obtain atomically thin monolayers. I think the most prototypical example of this is graphene. And actually, I think this is now very well established how graphene and the subsequent study of transition metal dichalcogenates, for example, has driven an amazing improvement of semiconductor technologies. But as a next step forward, we realized that we could actually do this very same thing, but with magnetic materials, in a way that we can isolate atomically thin magnetic layers and implement them into electronic devices. And this is an exceptional platform to access new physical phenomena, as we can test different spin models. We can also excite them by different means, for example, by light or gating. And they are also very sensible to strain or pressure effects. So I wanted to study some of these examples. And when looking at what was done in terms of materials chemistry, or what was the material database that we were exploring at the moment, I realized that most of the work was actually focused in transition metal three halides, which can be made for several halides, and they are all magnetic, but actually they are very ionic, meaning that they show pretty flat bands, meaning that the electronic conductivity is actually very, very low. So if we want to actually implement this material in a device and control it, for example, via an electric field or gating, we would like the electrons to conduce. So in order to try to tune the electronic properties of these materials, we identify that the combination of chalcogen and halogen anions actually can bring this mixture of properties. We see how now the chalcogen anions will give a more covalent character, and we have actually an anisotropic band structure where we have high conductivity along one direction while retaining the localization, which gives the magnetic order on the other direction. So we definitely wanted to make this compound. And for this, we go to the literature. And we found that one of the proposed approaches was to use this sulfur dibromide as a transporting agent. And apparently, this is a very robust synthetic procedure. I have to say, we did not try, we did not follow the procedure by heart, but we use a conventional round bottom flask. And after reacting the elemental sulfur and bromine and distill the product under vacuum, we could isolate our transporting agent. with this, we will then perform a chemical vapor transport reaction, and we could isolate large single crystals of this van der Waals material. So once we had our crystals, we could actually go to PSI and use all possible techniques that we could find there. But we could also, in collaboration with groups in nanofabrication at the University of Geneva, test the actual performance of these materials in nano devices and see how this combination of chalcogen and halogen anions was actually resulting in very anisotropic transport properties, which indeed opens up further functionalities, for example, to have independent transport along the in-plane directions. And in parallel, in our more conventional approach, we would also characterize how this, the presence of this strong uniaxial anisotropy in this material was driven complex dynamic correlations over a broad temperature range that we could unravel by combining complementary techniques. So after this stage, it turned out to me clear that van der Waals materials are an exceptional platform to access further functionalities. And indeed, beyond our work, for example, in this in the effect of combining anions to optimize the electronic properties of these compounds, there are also some examples of how can we induce further magnetic frustration in this system. Or we are also recently studying how we can use these van der Waals systems as optoelectronic devices for example, photovoltaic applications. And my approach to this, or our approach to this, is actually to try to implement these soft, low chemistry approaches to try to chemically modify these systems in a more controlled way. So for this, during the last year, we have been under construction here at the second floor. But after quite a bit of work, several visits, regular visits to the workshop, but also after some fun, we are now up and running. And we are trying to extend this background I show you to the study of new complex materials. And just to brief you, two of the main lines we are currently working on in the group. We still want to explore further quantum phenomena in complex oxides. And if we think about what would be the perfect platform for this physical phenomena or this quantum phenomena to emerge, actually the concept of frustration is one of the most promising ways. As a most simple example, if we think that we have a lattice where our magnetic atoms are arranged in a, for example, triangular motif, this means that our magnetic interactions cannot be all fulfilled at the same time, and this will create the coexistence of many degenerate states. This means that there will not be a single ground state that could lead to a stable magnetic order, but instead we will have this coexistence of degenerate states which not only coexist, but will cooperate and give rise to emergent phenomena. However, this is, from the physical point of view, very exciting, but from the chemistry point of view, actually very challenging. There is no real proof yet of a material that shows this phenomenology, and this is because any chemical perturbation to this system will actually select this ground state that we don't want to observe. So we are currently working on designing oxides which alternate in magnetic and non-magnetic layers, which will have an underlying frustrated lattice. And this has been something that Bastian and Christine and also Colleen have been working on as part of their bachelor and master projects. And they have actually optimized several families of compounds and grow single crystals out of them. And we are currently studying these compounds as part of our a more broad collaborative frame as part of the QMAT Lighthouse and in collaboration with PSI. And we hope to be able to study soon these materials at the upcoming European spallation source. So beyond this line or in parallel, we also keep very interested in modifying van der Waals systems. And particularly, we are developing methods to control through chemical substitution both the anisotropy and the dimensionality of these systems to access a more control in a more controlled way. In parallel, we are also trying to take advantage of the van der Waals gap in these materials to intercalate and deintercalate molecular units as a way to bring together extended solid-state compounds with molecular chemistry. And this is something that is currently ongoing work. It's part of the PhD of Sabina, and also Timothy has recently joined as a postdoctoral researcher. And that we are also developing thanks to the exceptional characterization tools that we have at the moment at the department. So I will not give much details on how this line is going at the moment, but we are for sure very happy to discuss. So if you find this interesting or you have any idea of a potential connection with your research line, please come talk to us. And with this, I think I would like to thank you for your attention and give still some time on the break for a coffee and perhaps discuss a bit more about this.